right?
Yes, and how I have divided my presentation is that in the initial few slides, I'm going to speak upon what is the use or what is the advantage to use, dampers and these devices. What advantages do buildings get? Because what is immediate occupancy and what is collapse prevention? So, by installing dampers, you reach a performance standard of immediate occupancy, which basically means that even if there is a very large earthquake and sea level earthquake, even then your structure will remain unharmed, and even non-structural damage will be very, very less. So you can immediately occupy the building and keep reusing it even after the earthquake. So these days the concepts of safety have undergone a lot of change world over, and I'm sure that these concepts are going to be very actively used in India also, in Nepal also, because ultimately we basically follow what is happening around the world, maybe a few years later, but we do follow them.
Yes.
What's about its use in bridges?
So in bridges, again, in buildings you use only dampers. In bridges you use two types of devices. One is called shock transmission units and the second is called dampers. So dampers work the same way as in buildings. They absorb the energy. But the shock transmission unit, how it works is that whenever there is a shock transmission unit, it locks itself. So which means, let's say, a bridge is having, so it will have 9 pillars and it will have 2 abutments. So if you have shock transmission units, then this entire bridge will behave as one unit. That means the seismic forces will get distributed in all the pillars and the abutments, and so it is a much better form of safety and of design also. But some bridges they don't use shock transmission units. They prefer to put dampers. So between the pillars, between the one end is connected to the pillar, other end is connected to the bridge deck, and whenever there is an earthquake, energy is absorbed and the demand from the earthquake gets reduced.
Yes. We have used lead rubber damper in some of the bridges.
Yes.
Just one type of pillar participating.
Yeah. Lead rubber bearings, you mean?
Yes.
The bearings, yes.
Yeah. So you are from Delhi or?
Yes, Delhi.
Now?
Our office is in Gurgaon, and which is Delhi NCR.
Right. So. And many guys from Mogeva and other suppliers, they frequently visit us.
Okay. Yeah. See, one thing which Nepal has to be very careful is, the soil. So,
Right.
Because there's a lot of amplification of seismic waves because of the soil, because it was an ancient lake bed.
Right.
So the soil characteristics are such that the waves will get amplified. So using bearings, you have to be very, very careful as to which bearing you are using. How is it going to affect the time period of the bridge or of the building? Because for Nepal, where the soil is a sandy bed, if you elongate the period to an extent where it coincides with the period of the seismic waves, then it will actually cause more harm than good.
Yes.
So that's the reason. Be careful. And primarily, you may have read some papers. Primarily, that is why people are saying that base isolation is going to work effectively because of the soil characteristics. Otherwise, because if you put a base isolator, you're going to go towards the elongated soil period, and that's going to cause further amplification.
Yes.
One amplification because of soil, and the second amplification will take place because of the frequency, soil frequency, and the base isolator frequencies coincides. So that's going to, yeah.
Still, people are joining, so let's wait few minutes, 1 or 2 minutes.
Yes, sir. Actually, we have the list. We paid for the program, and still they are not there. Might be we need to wait for a few minutes.
Okay.
We cannot wait long. Let's wait 1 or 2 minutes.
So Sandeep, have you been in Nepal already?
Yes. So yes, I spent quite a long time after the earthquake, and then when the Hilton project was being planned, so I did visit a couple of times. The plans got finalized. So.
It is interesting if Shruti Pathak is also here, right? Shruti bhai? Sandeep works in that side, right?
So Sudeep is online.
I have not seen him.
Okay, yeah. Sudeep is, I don't think, because I didn't see his name in the list actually.
Right.
How is the state now doing in Nepal? Have some of the buildings?
I think it's booming in Kathmandu.
Okay.
Because we are busy in designing maintenance.
Okay. So same in India, it was totally everything had, but now slowly it is again. Stopped. It had stopped. Just nothing was happening. So those projects have also started.
This will be very interesting and
Yes.
these buildings now.
Yes.
So, Subhash ji, now we have to edit. Please.
Let's start. Mandal sir.
Yes.
Sir.
And you,
Let's start now.
Shall we start? Okay, namaste and a very good morning to SEANep webinar session on knowledge analysis for design of camping system for buildings compliant with design procedure of ASC 7. Myself, Subhash Bastola, Joint Secretary of SEANep Executive Committee, Assistant Professor of Institute of Engineering, Pucho Campus. It's privileged to have given the opportunity to run the program. Now, the program, firstly, I would like to request President of SEANep Executive Committee, Associate Professor Dr. Bharat Mandal, to chair the program. Sir. Now, with the permission from the President, sir, I would like to start the program. Sir, shall we start?
Please, don't mind.
As you all are aware that SEANep is a non-governmental and non-profitable professional organization of Nepalese structural engineers with the aim of sharing and advancement of structural engineering knowledge, skills, experience, and thereby contributing to the development of the country. SEANep of protecting professionals' rights and prosperity of the structural. Yes. Also, it aims at promoting art and methodology regarding structural engineering. Okay, with these aims, SEANep has been regularly conducting various programs from its establishment date. Now, today, this program is organized as executive committee, which was formed last year. Now I want to develop this program. The schedule goes like this. We have a very dignitative person, Mr. Sandeep Shah, country head and MD of Miyamoto International India and Taylor Devices India. He has more than 32 years of engineering experience. His engineering career started with him getting commissioned in the Corps of Engineers in Indian Army in 1989. While in the Army, he participated in various specific projects. He started his master's degree in earthquake. He has in earthquake and civil engineering dynamics, and started his engineering consultancy. Mr. Sandeep has designed many iconic and complex projects, including the ATC Tower at Delhi, and specializes in design. Instrumental in introduce tanks and quick protection technologies in India to include dampers, isolations, mass dampers, and earthquake. His specialization is performance-based design using dampers both for new and existing building. His company from Gurgaon office is undertaking structural design projects in many countries like United States, Mexico, Peru, New Zealand, Haiti, and more. After that, we will have our highly decorated person, Mr. Vijay Jesse, so as a moderator. I hope he will guide his good views and add to the theme of the speaker. After that, we'll have question and answer session from the participants for about 10 to 15 minutes. I hope there are lots of questions on this, and our speaker will surely clarify as much as possible. And lastly, we'll end the program by closing remarks of the program. So, having said this, without further delay, I would like to request Mr. Sandeep Shah, today's speaker, to start the presentation. The floor is yours, sir.
Thank you very much, Subhashji. And it's my very proud privilege to be here on the invitation of Structural Engineers Association of Nepal. And I think I must thank Surid, who called me and was with me for me. We discussed about having a presentation in Nepal. Initially we were thinking of face-to-face presentation, but then my trip to Nepal did not work out, and Surid said, okay, let's organize something online. And I think Bharatji and Surid made it happen. So I'm very grateful to be here. And the idea of this presentation is to disseminate knowledge in whatever form is available. It is to assist engineers that they can undertake performance-based design, they can undertake nonlinear time history analysis. It is also for them to understand what is the use of this analysis and how they can save structural cost, at the same time make better buildings using this process. So with this as a brief background, I'll start sharing my screen. Okay, I hope everyone is able to see my screen.
Yes, can see, Sandeep.
Okay, thank you very much. We will start with a very small video just to understand what dampers do to building. So let's start with this video. So, this video is primarily to demonstrate two things. Firstly, both are flexible buildings. So, dampers do not add any stiffness to the building. So, the building remains as flexible as a building without dampers. But what happens the moment there is lateral shaking, moment the earth shakes and the building wants to move, the dampers absorb that seismic energy, and we're going to speak a lot about energy component, earthquakes and how the building behaves in this energy component. So the building with damper, firstly, there are two things. Firstly, it does not move much. Secondly, the floor accelerations. So floor accelerations are reduced tremendously. So the drifts, being a very small, it helps in having zero structural damage, and the floor accelerations being very very small helps that the non-structural components also stay unharmed. So dampers are protecting your structure and the non-structural components both. So let us assume if out of these two buildings, the building on the right, which is the building with dampers, was a very stiff building, right? Let's say it was walls on all four sides. So if I played the same video, that the building having walls on all four sides will also not move much, but it will have a lot of floor accelerations. So if it has a lot of floor accelerations, what is going to happen is the non-structural damage is going to be considerable. And these days we know that the non-structural component of a building these days is phenomenally more than the structural component. So structural engineers' work today is not only to protect, but it is also to protect the non-structural components. And the only way he can do it is by reducing the floor accelerations. So let us see where all a structural engineer may use dampers. So whenever he is targeting immediate occupancy or operational performance, which are the two highest performances for buildings, dampers find a use there. Buildings which target reduced floor acceleration to minimize non-structural damage. So it may be a hotel building, it may be a hospital building, it may be a high-profile residential building. But if you want to prevent, it may be an office building. Offices want to not stop doing business after an earthquake. So it's very important for offices to prevent structural damage and non-structural damage. Post-emergency buildings and are also which are going to be immediately be used after the earthquake. They also may use dampers. Buildings, now what happens is over a period of time, either your code may upgrade or your building may require a change. So the owner may want to retrofit and upgrade his building to the latest codes. Even over there, you find the use of dampers. Sometimes let's say you use a building for a warehouse, and after let's say 10 years you want to convert it into an office building. So the design criteria is like the importance factor and seismic component and the energy component of earthquakes changes, and you can use dampers over there to upgrade the building. Buildings may require drift control, so you may have seen buildings which are slender on one side and on one dimension is slender, the other dimension is large. So they need drift control in one direction. You can use dampers there. There are buildings which have torsional irregularity and they have a twisting movement in earthquakes. You can use dampers to prevent that. There are buildings which are on stilts, for various reasons, parking and things of this sort. And we all know as structural engineers that buildings on stilts are vulnerable buildings. You can use dampers there. And other buildings having vertical or plan irregularities, you can use dampers to overcome these structural deficiencies. Now, the structural design codes which are applicable and acceptable all around the world is ASCE 7 if you are designing new buildings, and ASCE 41 if you are designing existing. Dampers look something like this. When you make out from the outside, it either has one pin or has two pins. So a two-pin one is called clivus, and a one-pin one which has a base plate on the other end is called clivus base plate. So this is how the dampers look. These pictures show it in a very simplified way, the structure of a damper. However, the inside is pretty much very, very complex. So we spoke about when I was showing the video that the dampers will absorb the energy, and we all know that there are two types of earthquakes: design basis earthquake and maximum credible earthquake. Dampers are always designed for maximum credible earthquake, and sometimes under certain conditions, ASCE 7 provides for certain factors which even go over and above the MCE earthquake. Now, how this I have taken this from a typical project, a damper project, and if you see, this is the cumulative graph. It is showing the cumulative graph. The total area under the curve is the total seismic energy, and the pink component is the component which a component of seismic energy which has gone into the building, and the blue portion is the component of energy which is absorbed by the dampers. So you see in the design basis earthquake, the energy designed absorbed by the dampers is about 70%, and in the maximum credible earthquake, the energy absorbed is about 60%. However, so this is in terms of percentage, but in terms of quantum of energy absorbed, it is much, much higher in MC. So if I show you the y-axis, they are going up to, the energy component is going up to 40, so 40 e to the power 3 in case of dB, whereas in case of MCE it's going up to 160 e to the power 3. So the quantum of energy absorption is much, much more in MCE. Now, before we dwell into the technical part, what I have just spoken to you, going to just show you some examples. So this particular plan, if you see the building, it is slender in one direction, which is the y direction, and if you see the section, the structural engineer has put dampers in that direction so that he can control the drifts in the direction where the building is slender. This is a manufacturing facility, and floor accelerations play a very important part because of the sensitivity of the equipment in the manufacturing facility. So dampers have been put in this facility to reduce the floor accelerations below a certain value. Generally, if you see, it is ASCE 7 leaves it onto the structural engineer and the client to define the floor acceleration level. But for the benefit of all the structural engineers attending this webinar, you must target, under design basis earthquake, you must target the floor accelerations to be less than 0.2 G. So that's a very good value to target if you want minimal non-structural damage also to the building. Okay, so this is an existing hospital building, and they wanted to upgrade it so that the hospital can remain functional even after the earthquake. And if you see, they put some plywood boards over here, this image. I hope you can see my cursor. They put plywood boards, made a partition so that the hospital does not have to close down, and they installed in this. Dampers are also used along with base isolation. So this is a project. This is a hospital in Tokyo, and it is using dampers and it is using base isolators both. There are applications where there are areas where with very high wind conditions, as also very high seismic conditions. So this is a building in San Francisco, and very famous building occupied by Facebook, where dampers have been used both for wind also and for seismic also. This is a building in New York which is primarily using dampers for the wind, controlling the wind forces. There may be buildings, and this can happen in Nepal also, because the fault lines in the Himalayan kingdom are all over the place. So if you're having a building, important building being constructed near fault line, then there are dampers which are put in the main building. So you see all these diagonal elements you see over here. So they are put in the main building, and they are also put in the foundations along with the base isolator. So if you see this is the base isolator. It's a friction pendulum base isolator. This is a damper. So this is the plan. So, and you see, because such high seismic energy needs to be absorbed, that's the reason why you require so many dampers. Now, the ideal situation would be not to locate a building in this area, which is right next to a fault line, but sometimes the compulsions are of having a building at a particular place. So if those compulsions are there, then structural engineers can use dampers even to overcome those effects. Now, so what, in a nutshell, in a brief summary, what are the advantages that dampers offer? They improve the structural performance where and when needed. Code compliant buildings can be designed to lower cost. Now, why I'm saying code compliant buildings can be designed to lower cost? Because the ASC 7 has a provision where if you're using dampers, the building without the dampers should only be meeting the 75% base shear criteria, and without having any limit on the drifts. That means it should have enough steel that it can withstand 75% of the base, but that is, the drift will be controlled and brought into the code limits. Dampers are as good as new even after a MC event. That means even if there is a maximum credible earthquake event, and the earthquake that Kathmandu witnessed in 2015 was not a maximum credible event, was in fact much less than a maximum credible event. But let's say that there was a building in position with dampers at that time before 2015. The dampers would have been designed to maximum credible event, which is far in excess of what Kathmandu saw. So there is no maintenance after installation, at all required for dampers, and there's a certificate we give along with the dampers saying there's no maintenance required. The warranty of the dampers is 50 years. Now, how the warranty works is the initial warranty is for 35 years. After 35 years, we test about 10% of the dampers just to make sure that they are still functioning and intended the way we built it, and we extend the warranty by another 15 years. So the warranty, nothing happens to a damper. The damper life, we say, is 100 years and beyond. That's what we claim. The warranty, we don't mind giving a warranty of 50 years for it. Dampers are of aerospace quality. They are certified to that. So our dampers are the only ones in the world which reduce all the stresses, drifts, accelerations, and forces in all the structures, and also the barrier. Like before, all dampers are tested to MC maximum credible level in front of the contemplative if we send that to site. Now, the most important thing that structural engineers must understand is that they don't have any Secondly, they work for all types of earthquakes. So, they will work for a very, very small earthquake. Now, that small earthquake can have its epicenter nearby. There may be a earthquake which happens far away. So, by the seismic waves that travel to the city, it's very small. Dampers will still work in that. The dampers will, work in medium earthquakes, and they will also work in very, very large earthquakes. Over here, it is also good if structural engineers understand that the damper is configured to MC earthquake. But when we actually build the damper in our factory, we keep a factor of 2, which means that a safety factor of 2, which means a damper has a very high inbuilt safety factor, that even if the earthquake comes, it is much beyond the maximum credible earthquake. Even then, nothing happens to the damper. Okay, now let us get on to the design process. And for this, I have prepared 6 documents. The first document is nothing but, I have directly taken the criteria as spelled out in the ASC 7 code and the commentary, and I have cut, copy, paste and made a document so that it is a handy document that structural engineers can read the code clauses as they are in ASC 7. The second document is a very important document in which there is a commentary on each and every design and safety feature that ASC 7 talks about. This is the most important document that you can have. There is no parallel document that exists anywhere in the world. So I have not seen, and I'm in the business of dampers for last now 16, 17 years. There is no document in the world existing which gives you a commentary on how to design the damping systems and has elaborated each and every clause of ASC 7 to such a great detail as given in this document, which is the second document, which is commentary and explanatory notes. I will also request the structural engineers that they must read this at least 2 times before they start going and actually start to attempt designing of dampers in ETABS. The third document, I have prepared a file which is giving you screenshots from ETABS, obviously the ETABS non-linear version. So it gives you screenshots from ETABS non-linear analysis software as to how you need to undertake the damper analysis, damper design analysis. The fourth document is nothing but a single page file, and it talks about the minimum stiffness values to be input in ETABS, and I'm going to talk about this later when I explain the ETABS to you. I am also sharing with you 6 time histories of accelerations, and I will also be explaining in detail how you have to use these time histories. The sixth is an Excel file. It is an Excel file which gives you a time history analysis to design dampers. All structural engineers must understand it is an iterative process. So one analysis is not sufficient for you to design dampers. You may have to repeat the analysis about 6 to 8 times, and I will explain this in much greater detail to you subsequently with subsequent slides. But how do you start the first analysis? What values do you put in the first analysis? So this is a file that's going to help you. Now, all these 6 technical documents and a copy of the presentation which I am showing to you is already with the organizers of this webinar, and they are going to share it with all the attendees who are attending this webinar. If there is some document which you have not received or there is some clarification you want, please note my email ID, which is given here, Sandeep Shah, sandeep.shah@tailoredevicesIndia.com. Feel free to email me. I may not be able to respond to you immediately, but I try and respond within 2 to 3 days. Before I start showing you, the screenshots of ETABS, let us go. This commentary has got, first of all, it has got many clauses, and it goes into a lot of details. It is an unparalleled document which you will not find anywhere in the world. I'm sure, after this document has been released, people elsewhere in the world will see, and they will produce documents which are better and have more examples and more explanatory. And so it is, I feel it's a step in the right direction, where knowledge is being disseminated to structural engineers for undertaking sophisticated analysis. Now, I have not copied all the clauses here, but before we start with the design process and we start looking at how to design in ETABS, let us read a few important clauses. Okay, so in stage 1, that means stage 1 is before you start, this is when you are preparing your ETABS model, right? So you have to prepare, you have to have a ETABS model to start doing the damper design process. So if you don't have any building, or any ETABS model, means the same thing for us because we're discussing design now. Obviously, you won't be able to design dampers. So here we are talking about, what conditions should the ETAB model meet. Now, this clause, because it's ASCE 7, so it is applicable to new buildings. If it was old buildings, this clause won't be applicable. But what this clause says is, undertake linear response spectrum analysis to configure the structural members, which is the beams, columns, and we are now talking about the size, and strength, which is we are now talking about the reinforcement. The configured structural system should be able to fulfill the gravity load case as per the Indian Design Code. Now, why I have not changed this is because I saw that in Nepal also you follow the Indian Design Code. So the gravity load case, which is 1.5 dead plus 1.5 live, the building should be able to meet this. And also ASCE 7 warrants that the building without dampers should be able to withstand 75% of the calculated minimum base shear. If there are some discontinuities like extreme torsional discontinuity or soft story irregularity, then this 75% is replaced by 100%, but there is no limit to the drifts, like I explained. So you should have, if it's a new building, you should have a minimum, a building which can withstand a dead plus live loads, and then you can start your, and it should have strength to withstand, at least 75% strength to withstand the minimum base shear, right? Also, you must understand this minimum base shear is for collapse prevention. It is not conceived the 75% base shear, which is for collapse prevention, is a very small component when you are comparing to immediate occupancy period. So, if it's an existing building, then obviously existing building you are retrofitting it because you want to make it stronger. So this 75% clause does not apply to that. However, the gravity loads, that means 1 plus 5 dead plus 1.5 live, that is still applicable. So if you want to upgrade an existing building, it should at least meet the gravity load conditions. Before you start thinking of immediate occupancy or operational level performance. Now, ETABS has a very nice and fast way of doing time history analysis. It's called FNA, or fast nonlinear analysis. So we undertake fast nonlinear analysis in ETABS to configure the dampers. In FNA, dampers are modeled nonlinear, whereas the building structural elements are modeled linear. It's a quick way to perform time history analysis. You don't lose much time. Using FNA, structural engineers can undertake damper design without having time-consuming full nonlinear analysis. Stage 2 analysis procedure, as I mentioned earlier, is an iterative procedure of damper design. Probably, you will take 6 to 8 runs to finalize your damper. Also, after you finalize, after the structural engineer finalizes to his best knowledge the damper design, he will obviously get a specialist on board who has designed projects earlier with dampers, or he may get in a damper manufacturer on board, and the damper manufacturer will also run your analysis and check it that everything is in order. So it is additional check that happens so that there is nothing drastically wrong. Now, the combination of the seismic force resisting system and the damping system is permitted to be used to meet the drift requirements. So, as I mentioned earlier, the code, even if you are designing to dampers, how do you save cost? So, you first of all, you design only for the gravity loads, then you give it some strength for the minimum base shear. However, there is no restriction on the building drifts. So the building can move as much as it wants, but the dampers will be configured to control the drifts and bring it to the limits of the code. Okay, the seismic force resisting system without the damping system, as if the so we have dealt with this clause earlier, that it is 75% is the strength. However, if there are horizontal and vertical irregularities, then ASC 7 gives a penalty on those kind of buildings and says that please have the building without the dampers meet 100% of the seismic base shear criteria. However, the building can go outside the drift limits as defined in the code. Drifts you can control using dampers. That's what is the clause in ASC 7. The seismic base shear used for design of seismic force resisting system. Okay, so again, this is again trying to define to you what is extreme torsional horizontal irregularity or extreme soft story irregularity, which is basically the lateral stiffness is less than 60% of the stiffness of story above or less than 70% of the average stiffness of the 3 stories above. Damping device and all other components. What are these components? The steel components named the insert plates on which the damper is attached. The insert plates are embedded into the concrete. The anchor bolts, the gusset box, the gusset plate and the damper brace, which is required to connect the damping device to the structural system. They are all designed to maximum credible earthquake. So this was in the introduction I mentioned this to you. These are all designed for the highest earthquake force. Yes, that you need to undertake the nonlinear time history analysis for both. You are designing dampers to MCE, then why need to undertake design basis earthquake for DB, right? Now, the reason for this is all dampers are. So, if you design a building which is, let's say very stiff, and the dampers do not actuate in a design basis earthquake, so they can actually cause more harm than the benefit, because if they don't activate in a design basis earthquake, that means they're going to make your building more stiff. If they make it more stiff, the time period reduces. If the time period reduces, you go into the higher bracket of the response spectra. That means it's attracting higher seismic forces. So this is something which again structural engineers need to understand. Also, there are many dampers which will induce forces in addition to the earthquake forces in design basis earthquake. So, let us assume, you have a damper. Friction damper is a displacement dependent device, right? So and it induces a constant force. So let's say there's a friction damper and the slip load is 1000 kN. Now, which means basically that whenever the device is active, it will be inducing a force of 1000 kilonewton. Now, because the response of the device is in phase with the response of the structure, so even if your structure is at maximum stress, it will still be having additional force of 1000 kilonewton. So there are many dampers which induce higher forces in buildings, and these higher forces add to the already existing forces and need to be taken care of when you are designing your structural elements, which is your beams, your columns, your foundations, your walls, if any, things of this sort. So that is the reason why it is undertaken in DB and MC both. Dampers need to be compliant to multi-axis movement. So, like we all know, it will be what ASC 7 warrants is the damping device shall provide sufficient articulation to accommodate simultaneously longitudinal, lateral and vertical displacement of the damping system. Now, the longitudinal and the vertical displacements are complied by the damper stroking. But what happens to your lateral component? So many, because if that damper cannot articulate, the lateral component, it is not going to work under 100% efficiency. And there are many dampers and many damper manufacturers who do not meet this clause of ASC 7. And probably people up till now were not too aware that they need to ask this question to the damper manufacturer. But I'm sure, with wide publicity we are giving to the this document that I'm going to share with you, and I've shared with you. People are going to become more aware of these clauses. Point number 7: the minimum and the maximum damper properties. Now, this is a very, very important clause, extremely important, and it is seldom not understood in the correct perspective. We must all understand that the bottom line is dampers is a mechanical device. So it's a mechanical device, and which works in a certain way. However, what are structural engineers doing? Structural engineers are designing this mechanical device, using the mathematical software like ETABS, which understands only equations and matrices. And it only works with exact. 7 realizes that mechanical devices, may not be designed to exact mathematical equation, and so it has introduced something called as the lambda factor. Lambda factor is nothing but a variation from the ideal response. So the ideal, let's say, for fluid viscous dampers, the equation is F is equal to CV to the power alpha. So this is the equation, right? So you will get one value of F, which is the force, using C, velocity, and alpha, which is the velocity exponent, nonlinear exponent of velocity. Now, this is the ideal solution. Now, a very proficient damper manufacturer may be able to manufacture a damper which is 5 to 10% within this ideal location. However, ASC 7 says that you should not take lambda max less than 1.2, which means 20% higher than the ideal, and the lambda minimum greater than 0.85, which is 15%. So there is a variation in lambda minimum as 15% and lambda max is 20%. Now, both these values are important, as you are going to use both these values for designing of dampers. Lambda max will give you a higher force capacity of the damper. That means you need to use lambda. The lambda max will govern what is the force capacity of the damper. What will lambda minimum do? Lambda minimum will give it, allow the damper to stroke more, right? So if the damper is stroking, let's say with ideal it is stroking plus minus 50 mm, with lambda minimum it may stroke plus minus 75 mm. So lambda minimum will govern the stroke capacity of the damper. So that is what why you use lambda max and lambda minimum. Now, for velocity dependent devices, what property varies, right? So the property is C value, the coefficient of damping. Coefficient of damping, which is the property of the damper, that varies by 20% higher, gives you the force capacity of the damper, varies by 15% lower, gives you the lambda minimum, and that gives you the damper stroke capacity, right? Let's say a structural engineer is designing a friction damper. So then which is the property which changes? The property which changes is the slip load. So let's say the slip load is 1000 kilonewton. So you will have to use a slip load of 1200 kilonewton. Now that when you use a slip load of 1200 kilonewton, that slip load is going to induce different forces, much higher forces in both the damper attachments and also the structural members. So you will have to design your structure and your damper attachments to that value, and the lambda minimum is the you come 15% lower, which it will give you 850 kilonewton as the slip load. Now what 850 kilonewton slip load is going to do? It is going to make the damper move more. So your damper movement capacity of your friction damper will depend on lambda minimum, right? Okay. Nonlinear response history procedure shall be used for 7 sets of dB and 7 sets of MCM. Now there is a very, very important factor called as the damping system redundancy. Now some people, people should not misuse dampers in using just for the name of it. So let's say somebody wants to misuse dampers, so he just says he puts let's say just 3-4 dampers on each floor, and he says, oh, I have a damper. So what you can still do that, but if you are having less than 8 dampers on a floor, then you need to introduce a damper redundancy system, which is nothing but as adding 30% to the force capacity that you receive. That means, let us say you've designed dampers 1000 kilonewton, and you don't have 8 dampers on each floor. The dampers which you will have to procure should have the force capacity as 1300 kilonewton and not the 1000 kilonewton which you have designed, because of the damper redundancy factor, right? So this is a very important case. And also, because you are increasing the force capacity by 30%, so 1000 kilonewton becomes 1300 kilonewton. So 1300 kilonewton is going to have a higher velocity. So if it has a higher velocity, you will have to input that velocity and see what is the damper stroke. Now, a building may have components which can affect the stroking of the damper. That means the piston of the damper, how much is it stroking, the shock absorber, how much is it stroking, will let's say you have brick infill walls or hollow block walls, that's going to affect damper stroking. So these you need to input the stiffness criteria of these infill panel walls before you design the dampers. Similarly, basements will have retaining walls, so you need to input those, because again those will be very stiff structural components. So you need to model that in ETAB when you are designing the dampers. I have already explained to you these 2 examples, one with fluid viscous dampers and the second with friction dampers, when I was explaining the properties lambda max and lambda minimum. Okay, now let's come to the software that you use. ETABs, very, very popular software all over the world. Structural engineers use it very, very effectively. Now, because dampers are non-linear, So you must understand that you have to use the nonlinear version of ETABS to design your dampers. Now we will go through the steps that structural engineers need to follow for designing a damping system. Step 0 is that you have to start with the ETABS model. Now I'm not going to, it's whichever building you have. You may have an existing building or you may have a new building, but you have to have a ETABS model. Now in the previous slides that I showed you, if you recollect, we discussed that there has to be a minimum criteria that this ETABS model meets, and for new buildings it is that it should meet gravity loads and 75% of the minimum base shear without any limits on drift. For existing buildings it is only the criteria of gravity loads. So you have this model, you take it, you opening it in ETABS nonlinear version. The first thing that you need to define is the target response spectrum. Now also we know that we have to undertake analysis for both MCE and for dB. So we'll have to define the target spectrums for both MCE and dB. Now I have highlighted what the commands to be used by the structural engineer with red. So whatever is highlighted red, that needs to be changed using a Dropbox function by the structural engineer. So because Nepal is also functioning on the Indian codes, so we choose the 1893 and we say add new function and we say okay. Something checkbox window like this opens up. What do you do here? So I have named this as maximum credible earthquake target spectra, and you can choose whichever zone you want. I have chosen 4 over here. Now we're going to debate about why I am taking this importance factor 3, right? So we're going to talk about this. I'm going to just come back to it. And the next is you use response reduction as 1, right? Now the spectra, the earthquake response spectra, which is given in the codes also, is the 5% damped spectra. So this is the default value. You don't need to change this, right? Now let us say if I just put 1 over here. So what will ETABS do? ETABS will give me, as we all know, the design basis earthquake. But what am I wanting? I'm wanting the maximum credible earthquake, right? So I'm wanting the maximum credible earthquake. I don't want the design basis earthquake. So as per Indian code, how do you convert dB into MCE? There's a factor of 2. So if I put 2 over here, my dB gets converted into MC, right? However, now I take you back to a clause at the intent of ASC 7. And what is the intent of ASC 7? The intent is that dampers will be designed to remain elastic. That means the dampers and all its attachments will be designed to remain elastic under maximum earthquake forces. Now, so all codes other than the Indian code, when you are using the load case factor for earthquake, is 1. And it's for a reason, because if it's 1, then it's easy to relate the design process with the performance-based design process. But in Indian code, that's not the case. So we have, in one of the load cases, we have a factor of 1.5 earthquake. Now that 1.5 earthquake induces the maximum earthquake forces on the structure. So to be compliant to ASC 7, I need to take care of that factor of 1.5 which is there in the load case, right? So I multiply 2 by 1.5 and I get a figure of 3. Now this figure will give me a spectra which is the MCE target spectra. I click OK. Similarly, I design the dB target spectra. Now in dB over here, I have not used 2. That means previously we used 2 into 1.5, because this 1.5 is nothing but the load case factor in the Indian code. So for MCE we use 2 into 1.5. Over here we take out the 2 because it is a design basis earthquake. We only use 1.5. So now I have defined, I click OK. I have defined a MCE target spectra. I have defined a dB spectra, right? Now, once I have defined the response spectra, I need time histories. So there's a procedure to import time histories into ETABS, right? I have shared these 6 time histories with all the people attending this webinar. Email, as I said, will come to you from the organizers. If it doesn't, then you please apprise me and we will make sure that you get these time histories, because without these time histories, you won't be able to do the analysis part. Now, these are synthetically generated time histories. They are time histories which are extremely potent. You can use for varied soil conditions. How you have to use this, I'll explain in detail. So first, these are text files, right? These are text files and you need to import them into ETABS. So the first thing we need to do is import them into ETABS and see what is the procedure to do so. So I open one of the files in Notepad and it shows me something like this, right? So in the first line it reads time and the second reads function, and I know this is acceleration time history. I also see what is the difference between the time step, and over here if you see the time step, it is 0.02 seconds. So 0.02. So over here I have 0.14, over here I have 0.16. So my time steps becomes 0.16 minus 0.14, it becomes 0.02 is my time step. Now I need to do another thing. So I need to say, I need to copy all the points and I need to paste it into Excel. And I need to scroll down and see how many points I have over here in the time history, right? So over here I have 2183 points. So my 2182, because the first line is just a line mentioning time and function. So actually I have 2182 points over here. Now once I have noted this on a piece of paper, I then go to my my next step. So I say define function time history function. Now something like this is going to open a define time history. Now over here I choose from file and then I click add new function, OK, right? So if you see over here, because I'm going to import a file, so I need to choose from file. A box like this is going to open. So first I'm going to give it a name. So now these are just accelerations. So this is acceleration time history 1, right? It is still not MCE, it's still not DB. We don't know what these accelerations are because they're just random text, random time history files, acceleration files which I have given you. So when you are importing it, you are just giving it a acceleration time history 1 as a name. Then you browse and you choose the location where you have saved that file, right? Now these values are, when we opened it in Word Notepad, we saw that they were time and function values. So we click on the radio button saying time and function. Now if you recollect, the first lines was a text line, so we need to skip that, right? So we say skip. Now there were no extra characteristics in lines, so we say characters to skip is 0. And how many points did we have per line? We had 1 point, right? So we say free format, and this time history gets imported into ETABS, right? But you must understand, structural engineers must also understand this, that if this, what this will do is, every time you have to run the time history analysis, it will have to refer this location, right, for the time history. because it's importing it from text file. ETABS has given you a very simple way to embed this time history within ETABS. How do you embed that? You say convert to user defined. So you check this, the time history gets imported and gets embedded into ETABS. You say OK. Moment you say OK, you see this time history, the same time history is got embedded, and now you say OK. Now you have the time history. Now every time ETABS does not have to go to this file to access the time history. It has got embedded in ETABS. You repeat the same procedure for all the 6 files I gave you. So you will have acceleration time history 1 to acceleration time history 6. If you have some time histories of your own, please you're free to import that also, right? So now we have 6 time histories. Now what do we do? What is our step 3? Our step 3 is to convert the imported time histories into spectrum compatible ones, because you can't just use, a structural engineer just can't use any time history, right? The time history has to be hazard compatible. And what is the hazard? It's both design basis earthquake and the maximum credible earthquake. So you need time histories because you need to perform analysis for both design basis earthquake and time history earthquake. So you need to have both type of time histories. Now, how do you convert the imported time histories into DB and MC ones? So you say define function time history, right? So this function, this box again opens up. Now what you choose over here is match to response spectrum, right? Now we already have a target response spectrum. So over here, sorry, we already have a target response spectrum. So now we want our DB and our MC time histories. So we choose over here match to response spectrum. We click OK. Moment we do that, a box like this opens up. Now, first I want to define my design basis time histories. So I said DB time history 1, right? And I'm going to do spectral matching, ASC 7 procedure of spectral matching. So I use spectral matching frequency domain. Now, it asks you what is your target response spectra. So this is my design basis time history. So I am choosing design basis earthquake target spectra. And what is my reference time history? Is the acceleration time history 1. So this is the time history which I have. So you choose this. Now the only thing you need to do is match time history. So moment you say match time history, so if you see our original time history was the blue response spectrum, but our design spectra is the brown spectrum. So it reduces the time history from the original to the spectrum compatible time history, and that becomes our design basis earthquake time history 1. Now again, ETABS every time, if you don't want to ETABS to refer and do this calculations again and again, you just say convert to user defined, right? Moment you say convert to user defined, this will open up and it will get defined here. Now you need to use the same procedure to define design basis time history 1 to design basis time history 6, and also MCE time history 1 to MCE time history 6. What will happen in MCE? The target response spectra will become MCE target spectra. Rest everything remains same, right? So by the end of it, you'll be having 6 plus 6 time histories over here, right? Now, in this, these 6 you can make n number of combinations. In the example that I'm showing you, I've made 6 combinations. So one combination I've made is 1 2, the second combination 2 1, third combination 3 4 4 3, 5 6 6 5. You can also do 4 and 2 and 2 and 4. So you can keep making n number of combinations, right? Now the next process is define the damper property, right? Now how do you define the damper property. Now define section properties link, right? So when we click this, something like this opens up, and we say add new property. When we say add new property, a box like this opens up. Now I have named the property fluid viscous damper 1. You can name it anything, right? You can name it fluid viscous damper my project, fluid viscous damper X direction, fluid viscous damper story 1 to story 7, fluid viscous damper Y direction, anything. What you need to choose is damper exponential, right? So you need to make this damper exponential. Now why damper exponential? Because it will give you a non-linear fluid viscous damper. The direction, this is the local direction, that means the damper will stroke in this direction. So this is the local direction of installation of the damper. We choose U1, and we are going, like I mentioned earlier, we are going to optimize for non-linear dampers because they are the best way to design a damping system, and also they're more technically better and also cheaper, because the same dampers can be used for MC and for DB. So you choose non-linear, and then you click on modify, right? Now modify is going to open something which looks like this. Now we need to fill some values here. So how do we fill those values? So to start the first iteration process, this is an Excel sheet which I have provided you, and like it says on top, only input the cells marked yellow. The example I have taken is a new building, very sound. The column sizes are approximately 900 mm by 900 mm. They can easily take a damper force of 2000 kN. So I have decided to use a 2000 kN damper. So if I choose 440 kips, it gives me a 2000 kN damper, right? Now velocity exponent. Now like over here, it shows the damper equation. Force is equal to CV to the power alpha. This is what is so V is the velocity. Velocity will be induced by the earthquake. So we don't know what the velocities are. So velocity is going to be induced by the earthquake. Now this alpha value, which is the property of the damper, this is 0.3. This in 99% of the cases, or maybe 90% of the cases, will be 0.3. It will definitely give you, one of the best results. Sometimes you may also choose a value of like 0.4 or 0.5. In some cases, right? Now over here you see expected maximum velocity, expected minimum velocity. Minimum velocity generally always remains the same, which is the minimum, which is 0.05, which is 5 centimeters per second, a very, very low velocity. Like I told you, dampers will work in low velocity, in medium velocities, and in high velocities, and in very high velocities. Now what type of velocities can you expect? Over here I've chosen 0.4. So let's say the building was located in Kathmandu, and the building is not very tall. Maybe it is, let's assume, 3 stories high or 4 stories high. You can to start with, you can choose this value of 0.4. But let's say the building is a little higher. Let's say it is 10, 14 stories high, 15 stories high, right? Probably the interstory, because of the soil conditions that exist there, the expected maximum velocity may come down to about 0.25 or 0.3 meter per second. Right? This is guesswork I'm doing now. Why I'm doing guesswork? Because I need to guess a value of coefficient of damping that I need to use. So now what this file does is it calculates the coefficient of damping for maximum velocity. It calculates the coefficient of damping for minimum velocity. Then it kind of averages it out to some value, right? But because I want things to be working, the first iteration to be working well for me, I choose a figure of 2800 over here. I can keep wearing this, to see. And also why I chose this figure is because I wanted to use a 2000 kN damper. So if I use this value, it will give me an approximate 2000 kilonewton force. Now, this is all guesswork. It's just not going to take me a minute or a minute and a half in Excel. So this is just guesswork. So, but it's an intelligent guesswork. So I get a value of 2800, value of C as 2800 kilonewton second per meter. So now what I do is, this is the checkbox that will open for me. The first is stiffness. Now this is not the stiffness of the damping device. This is the stiffness in parallel, stiffness in series, which means stiffness of the steel brace which is attached to the damping device. I have given you this table. Okay, what if I put this as very flexible instead of, let's say, 533,000? What if I put it as 100,000, right? Now 100,000 kilonewton per centimeter stiffness is something which is very, very flexible. So what's going to happen when the earthquake comes and your building moves? This very flimsy steel rod is going to keep fluttering, and by fluttering, it's going to, the entire displacements are going to be absorbed in this flutter of the brace, and no movement is going to get transferred to the damper. So I need this element which is connecting my damper to the structure. I need it to be of some minimum stiffness value, which is given in the PDF that I have shared with you. So for 2000 kilonewton, 533,000, you put that figure from here. If it's some other damper you're choosing, you see the figure what's mentioned, you put it. From the Excel that I previously showed you, coefficient of damping, we chose that for my first iteration it should be 2800, and the damping exponent is 0.3. So we choose that and OK, and our damper is defined. Now the step 5. So step 5 is you have to draw these dampers in ETABS, and ETABS through its graphical user interface has made it extremely simple for structural engineers to do so. How do you do it? You say draw links. It will show you the property. Over here I've just defined one property, FVD1. If you've defined 3-4 types of properties, then you choose which damper you want to draw. And you take your cursor and you just keep clicking the points where you want to attach the dampers. Once you do that, the damper, you start drawing the damper. So the damper gets drawn in this particular. So this is just an example I've taken. So I've chosen one elevation and I've put dampers at these locations. Why I'm not using any damper at the basement level, because basement level also has the basement walls, which gives it extreme rigidity to this floor. And to save on cost, I've not put dampers here. Even if I had put dampers, they would work, but they would not be 100% efficient. So I've put the damper ground floor onwards. Okay. Now comes a very important process, which is you are now defining the load cases, the non-linear load cases which ETABS will run for you. And like I said earlier, these have to be MC load cases and they have to be DB load cases. Now how do? I do define, I do load cases, right? Now a window like this opens up for me. Now over here I say add new case. So moment I say add new case, another window opens up like this. Now over here I give it a name. So this load case is non-linear MC time history 1. So remember, this is your load case now, right? Now we are talking about the load case or the time history load case which ETABS will run for you. So this is different than the time histories. This is the load case now what we are defining. So the name I'm giving is a nonlinear analysis MC time history 1. I use time history and I use nonlinear FNA, right? So we discussed about this. It saves us time and it's a very fast, accurate and a good process to design the damping systems. Now over here I choose acceleration. So acceleration. I choose Now accelerations need to be as per ASC 7. You need to have accelerations in both the directions. So the first one is u1 direction and the second one is u2, which is parallel to each other, sorry, perpendicular to each other, that is x and y direction. Now over here I choose the function as MC time history 1, and over here I choose the MC time history 2. Just be very careful, you can't choose the same value. That means I can't choose MC time history 1 and MC time history 1 over here, because that's going to produce resonance and it will give you totally different results, right? Inaccurate results. Depending upon what units are there in your earthquake model, you will put the scale factor. So over here the scale factor is, I've just used is 9810, which is nothing but units for acceleration due to gravity. Okay. Now when we saw the characteristics of the time history, I made you note that number of points are 2182. So I'm telling the ETABS that ETABS needs to run the time history for up to 2180. And I'm also telling the ETABS that the time step is 0.02 seconds, right? So this is because that's what my time history is. So this is the time step that it needs to run. Now there's a very important clause in ASC 7 which says that when you are designing the dampers, the modal damping cannot be more than 3%. So you need to say modify and show, and you need to choose here as 0.03, and you say OK. So moment you say OK, your load case 1, which is a MC load case, is defined. Now similarly you define the dB load cases. Now the only difference over here is you choose the function as dB time history 1 and dB time history 2. Everything else remains the same what I showed you in the previous slide. So you have to do this seven times. You will have 7 load cases. Why there are 7? Because that's the ASC clause, and when you're defining damping properties, you have to average out these time histories, right? Okay. What is the next thing I do? Step number 7. Step number 7 is nothing but I click on run the analysis, and ETABS runs the analysis for me, right? Now after each run, the structural engineer is supposed to do some things, right? So even before extracting the results and importing them into Excel and trying to see the details, you need to see if your analysis has run well. So there are 3 things you need to check, because after each check you may tinker with the properties that you have defined for your dampers. So you may increase the coefficient of damping, you may decrease the coefficient of damping, and also you may play around with the velocity exponent, which we chose as 0.3. So you may take it to 0.4, you may take it to 0.5, right? So what are the properties that I need to see? So first I see is display cumulative energy component. So when I click this, a graph like this opens up. What I need to do over here for me to show this graph is I need to check in load cases. I need to check, click over here and choose either a dB time history or a MC time history, and it will start showing me this graph. Now what does this graph mean? Over here you can see the color coding. This is giving you the global damping or the damping energy absorption component offered by the structure, which basically means that the energy which is going into your structure is in this particular case is just about 30%. And this is the nonlinear viscous damping. The dampers are absorbing maybe about 70% of the energy. So this is what this graph shows. Now over here you can choose another dB load case, right? Or you can choose MC load case. So this is the load case that we have defined. Different load cases, it will keep showing you results. If this is giving you unreasonable kind of value, either showing the blue portion very high or showing the pink portion very high, it means there's something wrong. Either the properties of dampers are not correct, or there's something else wrong in the way ETABS is doing the analysis. like you see for DB, similarly you see for MC. And you see if these are graphs like this, that means your dampers are working beautifully. If not, then you go on the next step, and also it tells you that you need to go and check, change some values, and then run the analysis again. Okay. Now, what is the next thing you do? The next thing you do is, how have your individual dampers worked? Have my dampers worked? So you want to see how your individual dampers have worked, and they can be. You may have modeled 50 dampers, you may have modeled 60, you may have modeled 100 dampers. So how do you do? How do you check individual damper, how they have worked? Display, quick hysteresis, links. What it does is, it opens a box something like this. Right? Now over here, please choose MC load case. So over here I have chosen MC time history load case as MC time history 1. Now the way ETABS labels the dampers is K. So K and a numerical. So K1, this damper I have chosen is K1. You can click over here and choose any other damper that you need. Now it will, when you choose a damper, it gives you a hysteresis loop which looks something like this. Now this is nothing but the deformation, and this is the axial force. So this is the hysteresis loops produced by the damper, and the area between the hysteresis loop is the energy absorbed by the damping system. Now what you do is, has your damper stroke? So over here you see a stroke of 60, and over here you see little less than 60, and over here you see the force capacity is about maybe 1350, and over here you see the force capacity is about 1400, right? However, you are using nominal properties of the dampers, and it is producing this graph. Now if you recollect, we went through a lot of provisions where in certain conditions you have to increase these values by 30%, and in certain conditions you have to further, you take some enhanced limit over and above this, right? So this is normal result property. So when I use those safety criteria of ASC, this about 65 mm, may reach, 100 mm, and this 1350 kilonewton may reach 1800 or 1900 kilonewton. After I incorporate the safety provisions of, the lambda minimum, the lambda maximum, and also the redundancy factor, which increases my force capacity by 30%. So when I use this, it will give me a higher result. So ultimately, when I go and order the damper, it will give a higher result than what is being showed by these graphs, because these, you must remember, is the nominal structural properties, and those properties are giving you these values. Okay. So what is the third thing that you need to see? And this thing, let me tell you, is the most important. When people are undertaking performance-based design, please pay extra attention to this. If your floor accelerations are not coming under control, don't hesitate in doing and repeating the analysis another 5 times or even 10 times. But this single factor is going to make all the more difference for you, how your building is going to perform. Now, how do you check this? Okay, so you go to display, you say show tables, right? A box like this opens up. So what you do over here is analysis results, joint output, velocity and acceleration, diaphragm accelerations. So this is going to give me floor accelerations. Now all other items I'm going to put 0, select load patterns I'm going to put 0, but in select load cases I'm going to use DBE. Now just remember, I'm checking, what am I checking? I'm checking floor accelerations, right? Floor accelerations, if anybody recollects what I mentioned right in the beginning of the lecture, I said under design basis earthquake, please try and keep the floor accelerations to less than 0.2 G, right? That's the level that you want to look at, because achieving immediate occupancy, let me tell you, is very easy. You will do it. Achieving this is a much more difficult criteria for the structural engineer. Actually, once you have achieved immediate occupancy, you may come to us and ask us for help and love to optimize the floor exhalations. Because supposing your floor exhalations are not getting optimized, you may even come to us and seek our help, right? So you choose these 6 load cases, dB load cases, and you say okay. But when you say that, table like this opens up, right? So it gives nothing but a story, different stories. It gives the load cases, and it starts giving you acceleration in X direction and Y direction. Z direction you need not consider, but X and Y is what you need to see over here. And if you see, I've just arbitrarily taken some points. This is dB 5, and this is dB 4, right? And this is giving me about 0.15 G, and this is 0.14 G, right? And what is the criteria that we have to achieve? Is 0.2 G. However, that criteria of 0.2 G is the resultant of these two. Right? We come as 0.18 or 5 or something like that. And that is the value that I'm telling you, which you must try and keep. Less than 0.2 G, because it will not only ensure, and if it's a new building, you will try and use dampers of 1500 and 2000 kilonewton. Okay. We have seen the damper process. Before I go into the next phase of my presentation, I'm going to show you a brief video, and probably I will also, have a break for a minute. So I'm going to show you a building where the structural engineer has designed the dampers and the installation of dampers is taking place. This building is in Peru. Okay, there you go. So we have seen, we've seen how to design the dampers. Now the dampers, like I mentioned, you can use for various purposes, and this particular building has a soft story, like you can see, and he's used dampers to overcome the soft story, so you can very easily incorporate the dampers in existing and new buildings also. Over here, this is a new building, and the dampers have been used to improve the seismic performance. Each one of you will be getting a copy of my presentation, so you will get everything that is in my presentation. You will be getting it, for you to have a look at these. This is dampers used for seismic retrofit. This is to control floor accelerations. This is again to upgrade the building to the latest code. So the code changed, and this was an old building. You can make out from the way it is built. So they upgraded the building. They put dampers there. This is an office building, and they wanted to make it immediate occupancy. It gives a very high rental value. It also adds the value of the property when you are selling it in the market. The office building was designed to immediate occupancy standard using dampers. Showing you a few pictures, I'm going to now cover a very quick case study of a building that was upgraded using non-linear time history analysis, which is called New Udan Bhavan, housing the GMR group located near Delhi airport. So the big square building you see in the background is the building that was upgraded. What I did and what I explained to you is made a ETABS model, put the dampers where I wanted to put them. Location of dampers is decided. When it is being decided, there's an interaction with the client, and there's also interaction with the architect. So you need to meet both the functionality. If you put a damper in a particular location, that functionality question is going to be answered by the client himself, who is going to occupy and use that building, and aesthetics are going to be addressed by the architect. So you need to have a discussion process in place to decide the locations of the dampers. Now, before we get on, I mentioned to you that you can design new buildings to immediate occupancy. You can also upgrade existing buildings to immediate occupancy. And let us see the definition of immediate occupancy. The post-earthquake damaged state in which only very limited structural damage has occurred. The basic vertical and lateral force resisting system of the building retain almost all of the pre-earthquake strength and stiffness. The risk of life-threatening injury as a result of structural damage is very low, and although some minor structural repairs might be appropriate, these repairs would generally not be required before reoccupancy. Right? This definition is a universal definition used by you're using any system to upgrade your building. But the system we are talking about is today the most advanced existing in the world. So what a structural engineer is actually targeting by using this system is zero structural damage. And also structural engineers is targeting minimal non-structural damage by controlling the floor accelerations. So what I have shown you is probably much higher than this. What does the minimum code criteria state, right? So if you're not doing performance-based design, if you're only designing to the minimum intent of the code, then you get a collapse prevention building. The building will not collapse. However, what is the performance of the building? The post-earthquake damaged state in which a building, which a structure has components damaged to an extent that it may have no margin against collapse, but it continues to support gravity loads. The building is on a verge of partial or total collapse. Substantial damage to the structure has occurred, potentially including significant degradation in the stiffness and strength of the lateral force resisting system and large permanent lateral deformations of the structure. So, in the beginning, we tried to talk a little bit general, and I feel it is one of the duties of a structural engineer to explain to the client when he is doing due diligence about the forthcoming project, to explain to him, what a minimum code standard is, what an enhanced code standard is, and what kind of advantages he can gain, by switching on to a higher performance standard. What, in my personal opinion, I have seen is that if at the early stage the client learns that he can, with a very insignificant additional amount of money, reach a level which is giving him kind of a guaranteed protection and so much enhanced safety, the person tends to tilt towards a better performing building. Now, in this particular building that I showed you, the client gave us a number of challenges. So he said, listen, we have an existing building, but that building needs to be operational at all times. Don't expect me to be non-operational. I'm not going to vacate the building. Also, please do not disturb my interiors. I don't want, minimum disruption is allowed, but I don't want you to start breaking up my entire building just to put dampers, because to do up the interiors again is going to cost me a lot of money, and I don't want to spend that. So this is one of the dictats the client gave us. He also told us that I'm not going to stop office function. So you have to work in key locations. Please plan your work in such a manner that I don't have to stop office function. And the quality standard that he was willing to accept was nothing less than 100%. No timelines, to be over, to be not met. We had to meet all the timelines of the project. And in addition, he said, I want the cost to be the least even if I compare it to the conventional technology. So he said, let me compare this, to jacketing of columns, or to concreting, fiber wrap of columns, whatever of my beams and columns, whatever I have to do, or adding shear walls to the building, making some new foundations. If I compare my cost to those technologies, I need to be cheaper. However, the client said, I'm going to give you the benefit if you cause me these disruptions, because if I save on cost on redoing my interiors, it's added advantage. So I'm going to see overall cost of project. I'm going to also give you a benefit if I don't have to vacate the building, because if I have to vacate the building, then I'm going to pay rent somewhere else. So if I'm going to stay in the same building, that's advantage. And if my building there's no disruption to my office working, then again it's advantage, because if I move to some other temporary place, I may not be able to function with 100% efficiency. So this was the criteria set by the client. We made the analytical model, put the dampers. We chose the seismic hazard, like I showed you in the ETABS presentation. We matched the time histories to the spectrum. Each component has X and Y component. Like I told you, we defined the load cases, time history load cases. This is the kind of loops. These are the loops, time history loops that we got. Energy dissipated by the dampers. We absorbed in this particular project, about 60% of the seismic energy. So under the blue line is the energy. That time ETABS used to show graphs like this. Now the graphs have changed. They are the ones which I showed you in the ETABS presentation. But when we did this project, ETABS used to produce graphs like this. So below the blue line is what energy was absorbed by the dampers. The area between the blue line and the red line is the energy which went into the structure. So we achieved immediate occupancy by far. The drifts were well within 0.8%, and even the base share we achieved about a 25% reduced base share. So the building became a very, very high performing building. When we were coordinating with the architects, the architect wanted to see how it will look after the building is finished. So the facade of the building had certain elements built in. So this is the figure below shows how we installed the dampers. Figure above shows how, when you look at the damper, how it's going to look. And this is how the dampers look. This is how we installed them. It's because just because of certain facade elements which exist. This is the rear elevation. So you see below is the how we fix them, and above is what you see, left side and right side. So we kind of showed these elevations to the client and his architect, and they say, yeah, it looks decent, please go ahead. When that was done, the dampers started getting manufactured. When the dampers were manufactured, the client came with us to the facility so that we do the testing in front of him. Testing is totally automated, so there's no human angle to it. We put the damper in the test rig, we switch on the chemistry, and the hose to the damper is fed automatically. The graphs and everything is automated. There's nothing you need to do with hand. And by the end of it, a graph and a damper certificate with all the technical parameters gets printed, and those test certificates are signed by Taylor Devices, and they are carried by the client. Now, just to show you a few pictures, these are facade elements. That's the reason why you're not seeing what is behind this facade element. So these are some pictures of the building where the dampers were installed. They look beautiful. You can install dampers anywhere. They don't look ugly at all. Now, having seen this case study, let me also tell you there are hundreds of ways to install dampers. Damper works wherever there is a differential in velocity, right? So whenever there is a velocity difference between 2 points, a damper functions. We don't need much of displacements actually. Dampers start functioning even if there is displacements of 1 mm. That's how low the displacements can be, and the damper will start absorbing its energy. I have tried to compile some images to show you some main types of damper configuration. So over here, if you see, the steel brace has been replaced by a concrete wall brace. So there's a concrete wall over here which is attached to the beam. It is not attached to the top beam. It is attached to the bottom beam, not attached to the top beam. Attached to the damper is attached to the column. Similarly, there's another concrete brace protruding downwards but not touching the beam below. There's a damper here which is attached to the column. You're going to get all these slides. So all attendees of these webinar are going to get all these slides with them. You can have dampers within shear walls. So you can install dampers like this. So this becomes a damped shear wall. So residential project where it's a new building, and you want to increase the efficacy of a shear wall, you introduce dampers within the shear walls. So they become like this. You can just put them conventionally with steel chevron brace or something like this. So over here it's having 2 dampers placed horizontally with a chevron brace. This is a chevron brace, but the dampers are in diagonal to each other. So if you see the chevron brace, but dampers placed diagonally. This is again they're not continuous. So what I want to kind of explain to structural engineers by the medium of this image is that as far as damping system is concerned, unlike friction dampers, if you're installing friction dampers, they need to be all the way from the roof till the foundation. They need to be continuous. You can play around with fluid viscous dampers. The reason for why friction dampers need to be continuous from top to bottom is because they act nothing but as a rigid element. They act like you put a shear wall over there. So if you're putting a member which is rigid, it needs to be continuous, because if you give it, even if you give it discontinuity in one floor, it will introduce vertical irregularity, what I spoke of earlier, which is 60% of the floor above, the stiffness of the floor above. So let's say I have friction damper on the above 3 floors, but I don't have on the 4th floor, on the floor below, and I have it again in floors below. So this floor is going to become a weak story. It is going to introduce to me, in this figure, it's going to introduce a structural deficiency. Nothing like that with fluid viscous dampers. You can pick and choose the locations where you want to have them. So you want to skip a floor, you're free to do that. You can have them like simple diagonals, if you don't require the dampers on above 3 floors, because putting every damper is some added cost. So if I was to put friction dampers, I had no option with me but to start from roof and go all the way to the foundation. Fluid viscous dampers, the dampers do their work, for the bottom 4 floors. You don't need to put them on the above floors. So it's as simple as that. Over here, again, it's a chevron brace, put for limited number of floors. Over here is an inverted chevron brace. Again, I played around by not putting them continuously. This is again, a kind of damper which is being put where I have not used steel brace. I've used a concrete brace. So when and each brace is having 2 dampers placed horizontally. Various configurations, and there are much more. Now, very quickly in the next 2 minutes, I will show to you, what happens. Let's say you decide to upgrade an existing building using dampers, and the building is something similar to the scenario that I'm showing you. What are the different stages? So dampers, they arrive on site, and the structural engineer goes and inspects the dampers that they have arrived in the sound condition. There's no damage. These are the kind of damper brackets. These get prepared in a steel manufacturing facility, steel fabrication facility. So these are the brackets, damper brackets, and these are the anchor bolts. The structural engineer has chosen to put the damper in this particular location. Now, I like showing the slide in giving my presentations, and why I choose the slide is because this is a very, very stiff and a rigid portion of a building. So if you see, there's a beam, there's a huge column, and also there's a concrete wall, right? So why is the structural engineer putting the fluid viscous damper here? That's because fluid viscous dampers are dependent on velocity and not on displacement. So I made this point initially, making it again by this slide, just to show you that dampers can be installed in very stiff locations also. I've shown you examples of flexible location. Now I'm showing you example of a very stiff location. So you anchor the vertical reinforcement, and you also put the horizontal. So don't feel there's no horizontal reinforcement. So over here, just because it's not showing, so you put the vertical reinforcement and the horizontal reinforcement, and the reinforcement will go right all the way up to the plate, the base plate level over here, which is this level, right? The damper is, these are the anchor bolts which will get embedded. So you put the formwork, you place the reinforcement, you put the formwork, and this is a gap, and then you pour concrete in it. After the initial setting time, you remove the, you let it set for a few days, then you remove the shuttering, and you get a damper brace. Now you see this damper brace is not connected to the roof, right? It's ending here somewhere, and these are the brackets. And over here, he's kept a huge gap between the beam and the wall, the concrete brace. However, that's because in this particular location it does not matter. But let's say you're doing it in locations like residential building, we can minimize this gap. To possibly we can lower this to 3 times lower than what you're seeing actually. This is my email ID. I hope I have done justice to the topics covered, and so I am going to now get back to you. So,
okay, thank you, Sandeep sir, for your presentation, for a wonderful presentation. Actually, we are overwhelmed by your presentation in detail on those dampers, use of dampers, and the special provision on ASC7, along with the one-to-one step on the TAPS procedure. Even we have you have shown a case study. Thank you so much, sir. Now we have highly decorative personality, Dr. Vijay Jesse. Dr. Jesse did his PhD in structural engineering from Fuzhou University, China. Postdoc in bridge engineering from Civil University, UK, and postdoc in bridge engineering from Yonsei University, Korea. He is a visiting scholar in Northern Illinois University, USA, and now he is working as a director in Quality Research and Development Center in Department of Roads, Government of Nepal. Sir, please go ahead with your views.
Okay, thank you very much, Subhas. Respected Chair and Presenter Sandeep, and respected personalities here and participants. Thank you very much, Speaker. You congratulations for your presentation. So useful presentation and so elaborative. You cover so many aspects from design to real application in the field. Damper is an element which can add to a system to provide forces which are resistive to motion and thus providing a means to energy dissipation. Right? We study in the structure dynamics. And we also remember we study the equation mvd double t cv dot plus t plus kbt ft. So damper is always there for we structure dynamics students. So moving to the today's presentation, our presenter he shared us many things. At first he gave us the importance of dampers, and you know we are in an earthquake prone area, and even now we are just starting use of damper in some buildings, but we have a big area for the future because we are in a very seismically active area. And we are moving to high-rise building these days because we don't have much space in Kathmandu and we have to go up, right? And also in the bridges, I work in Department of Roads, and we are having many problems, vibration problem in the bridges. We remember Narayani bridges, right? If we stand in that bridges, we all scared due to the vibration. So it is time we have to think for the dampers and energy dissipators for our bridge structures also. And I quickly like to recap to his presentation, today's presentation here. And at first, the presenter give us the brief importance of dampers. And in the same way, he gives the main provisions in ASC7 provisions. He gives us that thing. And in the ETAPS, it is a very famous engineering software we are using in Nepal also for building design. After SEAP 2000, I think we are using ETAPS here. And he gave us the steps to model the dampers in the ETAP. Like, for example, he used the define the target response spectrum and import time history, acceleration time histories, and convert the imported time history into a spectrum compatible to be used in the ETAPs. And the next step is define damper properties and drawing dampers, defining time history, load case, and he's so elaborate. That is very useful for we design engineers here. And run ETAPs and display the results, which is the important thing which we have to see. As we saw that the main thing in the damper is we have to see the energy trap and how much hysteresis we got, and it is very interesting about the 60%, more than about 60% energy is absorbed by the damper, right? It is very interesting to know these things. So we have just started damper installation on few buildings in Nepal. We have a big area in the future, and I hope all of our participants get a lot of knowledge for damper design and installations in many things. And at last, I have few questions on it. So I like to take some questions here, and maybe many of our participants they are thinking about these things. So if I cover these questions, it is okay. Otherwise, the participant will ask the question.
Yes, I think some participants have already typed some questions.
Have a question. Yes.
Yes. So if you can ask the question, and I will try my best to answer them.
Okay. So my first question is about the cost aspect, right? I'm a client also, and many clients they might have interest about the cost. How much the percentage of building cost? Let us go in some typical building, right? About 10-story building. About how much percentage of total building cost?
So if I am designing an immediate occupancy building, so let us assume I'm designing an immediate occupancy building.
Right.
The damper will add about 350 rupees cost per square foot. Now, so I'm talking in Indian rupees, so you need to convert, right? However, because I showed you that the damper is going to reduce the forces in columns and shear walls, it is also going to reduce steel. It is also the drift limits, are going to be taken care of damper. So you will save to the tune of maybe 100-150 rupees in the structure.
Right.
And so your net effect on building may be 200 rupees a square foot. So, and you get an immediate occupancy building, right? Which is absolutely great.
Right.
So you can calculate in percentage terms, and now again, structural engineers. This is a very nice question you asked, actually. Structural engineers, the way our mind works, we only calculate the structural cost, right?
Right.
So let's say the structural cost is 2,000 rupees a square foot. All our calculations is 2,000 rupees a square foot, right? Now, if I showed you all my slides, I gave very specific values that you please keep the floor accelerations less than 0.2 G, and your non-structural components will get protected.
Yes.
So if your building is 2,000, structure is 2,000 rupees a square foot, your non-structure is at least 4,000 rupees a square, maybe more.
Right.
And your damper is going to protect this entire 2,000 plus 4,000, 6,000.
Right. Yes.
Right?
Yes.
So I hope I've been able to.
Yes. Good. And yes, Sandeep, my next question is: we recently update our building code in Nepal. So now we use MVC 105 2019.
Okay.
So maybe you constructed more on IS code. So maybe we have to little bit change our setting in ETFs to use our NVC 105.
So again, I was not aware of it because if I was aware, then I would have changed my presentation accordingly. The only difference in my slides is when you are choosing the target spectrum, you need to choose what exists as per Nepalese code.
Yes.
So rest everything remains same. So there is no change in anything. But the target spectrum, when you are choosing, you have to choose the MCE target spectrum for Nepal and the DBE's target spectrum for Nepal.
Yes, that we have to change.
Otherwise, everything remains same.
I think so. Thank you. And my one of the last question is about the time history, right? You use the you source your time histories there. So for a real use in the building, maybe we need site-specific time history. What do you think?
See, site-specific time history, if you are building a dam, if you are building a nuclear power plant, I still understand you will go through that effort. If you ask me, site-specific time history for doing dampers is not required.
Okay.
And I'll give you the reasons behind it. The reason behind it right in the when I was showing you the USP of dampers, I showed you a graph and I told you that these dampers function for very, very small earthquakes, for middle earthquakes, for high earthquakes, and for very high earthquakes, equally efficient. Right now, what I like is if a structural engineer has optimized his dampers correctly, he need not worry whether the earthquake is very, very small, medium, large, or very large. The damper will do its job beautifully. You are now talking of a technology which is the most advanced in the world.
Yeah.
So when I like to give my model to a peer reviewer, I will give it without the time history. I'll tell him, you choose any time history you feel like, and you put it in this.
Yeah.
And that's the right way to do it also.
Yeah.
So when a person is reviewing the model, he should use different time histories.
Yeah.
I have given you a resource so that a structural engineer does not feel hindered that how will he start the design process. It does not mean you need to use that time histories. You can use any time histories available in the world. And when you give it to a peer reviewer, please don't give the time history. Just tell him, I have optimized the damping system. Now you can put any time history in the world. My building will work beautifully. And it will meet all the conditions given.
And instead of time history, can we use the response spectrum?
No. Okay. So there was again this question good you have asked, because this question is already covered. Somebody has asked this question, and yes, it is asked by Anish Sakhya. Can we use non-linear static analysis instead of non-linear time history analysis to design the damping system? And I'm afraid to say answer is no. See, don't get afraid with the words non-linear time history analysis. I've shown you how simple it is, right? You need to sit with a cool mind, sit for 3 to 4 to 5 hours, and you will start doing non-linear time history.
Right.
So don't, you see, dampers are non-linear elements. But why they are non-linear elements? Because I showed you velocity to the power alpha, and for the example I chose alpha as 0.3, which is non-linear. So if you want a non-linear element to work in your building, obviously you need to do a non-linear analysis. Why a static analysis won't work, like Anish asked? Because you need to capture the work done by the damper for the duration of the time history. Now, if you are doing a non-linear static analysis, pushover analysis, you will not capture the work done over a time period.
Yeah.
That is why you cannot use that analysis.
Use the velocity.
So you have to use non-linear time history analysis.
Okay. Thank you, Sandeep. So at last, the in nutshell, the building is required to have a performance objective. Every building. So we should control the structural roof, maybe roof displacement, inter-story drift, reduce base shear. So the damper is used mostly for this performance objective. So at last, I am very happy. Sandeep Shah also graduated from the Sheffield University, UK, right? So,
Yes.
Yes, very interesting to know we are from the same university. Actually, I graduated in 2011.
Okay.
Yes.
I did my master's very late. I went for my master's after I had work experience of 14 years. And I completed my master's in 2005. So it's been a long time since but I already had 14 years experience when I went for my master's.
That's good. Okay, thank you very much, Sandeep, and thank you very much all participants. So that's all from my side. Thank you very much.
There is one more question, and if I can read it. So this question is from Prayush Raj Bhandari. I don't know if Prayush is the same person who was with me after the earthquake, going from one building to the other.
I think he's the same person.
Yes. So hi Prayush. It really makes me feel nostalgic to read your name. So Prayush has asked me a question. how much does the orientation of dampers affect the building performance? Okay, so very good question. As we know, earthquake components are in both direction, X and Y direction, right? And so you need to have dampers in both directions. And it is covered in the ASCE clause. So I have covered it when I am giving you your commentary and elaboration on the ASCE 7. I have covered it there. However, to answer the question, dampers need to be in both the directions. Also, you need to distribute the dampers on both sides of the center of mass and center of eccentricity. So let us say the center of mass is located at one particular point, and you are looking at X direction. So dampers need to be in X direction in both sides of the center of mass. Similarly, if you look at Y direction, the dampers need to be on both sides in Y direction of the center of mass. So you need to distribute the dampers. So very good question, very important question also.
Subhas, maybe you take the session and ask other questions.
Thank you, Vijay sir, for your remarks and actually inspiring words on the use of dampers in future and the start of the question answer session again. We have more question, I think, on the message box. Oh no. Actually, the question answer session has already been started. Are there any more questions from the participants over here?
Yeah, I have.
Yes, sir.
Sandeep, I have few questions.
Sure.
Since we are designing for, say, for example, immediate occupancy,
Yes.
then does it mean we don't need to use importance factor? In conventional design, importance factor is used for this purpose.
Correct.
For example, immediate occupancy. So, can you explain this?
Yes. Very, very super question asked by Surit, and I have explained this again in the ASCE 7 provisions where I have given you the elaboration document. However, let's understand this. So let's say your building has an importance factor of 1.2, 1.5, 2, but as far as non-linear time history analysis is concerned, it does not make a difference. You need to just put the importance factor as 1. Now, why do you need to put it as 1? Because those importance factors are applicable for response spectrum analysis, because response spectrum analysis is an implicit method of analysis, which means
Correct.
that the code is assuming that if you will use a factor of 1.2, you will meet life safety. If you will use a factor of 1.5, you will meet measured occupancy. Code is it's an implicit form, but non-linear time history analysis is not doing that. It is explicitly calculating the performance. So, if the plastic rotations are less than 1%, you are already in immediate occupancy. If you want better than immediate occupancy, like I showed you the example, I actually chose a mark of 0.8%. So you choose the plastic, if it is between 1 to 2%, you are in life safety. If you are more than 2%, you are in collapse prevention. So, sorry, you are
immediate occupancy.
No, if the plastic rotation is less than 1% immediate occupancy,
Okay.
1 to 1.5%, you are in life safety. So these values are defined in the ASCE document itself. So to answer you, importance factor is not to be taken in account when doing explicit time history analysis.
Okay, thank you. Next question, I have one more question.
Yes.
There are already a few questions on the orientation, so I have questions similar. What is the most effective placement of dampers? Orientation wise, you mentioned it's required in both direction, X and Y direction, and maybe symmetrical to mass or symmetrical to stiffness. I don't know, maybe.
Yeah.
My question is, what are the 2 points? Because you shown diagonal dampers also, you have shown horizontal dampers also. So now I'm confused. How should we decide 2 points of the dampers?
Okay. So, if your question,
For example,
now,
can it be just below slab? For example, can it be?
no, you see why you need to have some element joining the roof and the floor, because you are working on the difference in velocity between the floor and the roof. So the damper, needs to at least join the 2 points somehow. Whether you joined it in a horizontal way or you join it in a diagonal way, that's left to the engineer. But you need to work with the difference in velocity between the roof and the floor.
Got it.
Right? And sometimes you even go 2 floors or 3 floors. So sometimes you install a damper which is at one end connected to let's say a floor, 3rd floor, and the other end is connected to a ground floor. So the damper length is 3 floors. So there are even those kind of cases. Now, if you were to ask me, if it is a metal yield damper or a friction damper, then they do not work very efficiently in certain positions because they are displacement dependent, right? So because they are displacement dependent, they don't work very efficiently in certain locations. Let's say, for example, the core of a building. They will not work efficiently there because the movement over there is less, and these dampers are displacement dependent. But fluid viscous dampers are not displacement dependent. They are velocity dependent. So they work equally efficiently everywhere. So if, let's say it's a tall building, 15-story building, and you want to have a damping system restricted to the core, or you want to have some dampers in the core and few dampers on the perimeter, you can have all those permutation combinations. It is an iterative process. So like I told you, the damper designer will have to conduct different analysis just to see which is a better suiting situation for him.
Okay, thank you.
Okay,
That's all.
as we are already running out of time, are there any one question? I think I will take one more question if there is from the participants.
So
Okay.
I think I've covered all that is in the chat box.
Yes,
I
sir.
think,
You have already covered from the chat box. I would
yeah, Prayush has asked another question saying orientation as in bottom left or top right, and bottom right to top left. So like I mentioned, Prayush, I answered Surid, it does not make a difference much for us because our dampers are velocity dependent. So left to right or right to left, it does not make any difference to us.
Yeah. I think this is Pratyush Raj Bhandari, not Pratyush Jha, maybe, right? we talk in the building. He's different person, I think.
Okay.
Yes, sir. Okay.
Okay, now I think I will end myself by requesting our chairperson for the closing remarks and to conclude the session. Sir.
Thank you, Shivaji. Thank you. First of all, I am thankful to all participants, our today's expert Sandeep ji, our Vice President Dr. Vijay Jaisi, and our Founder President Dr. Sandeep Shah is also with us. So actually today's speech was very, very important and attractive to we designers of the growing cities. In future, they have to use the dampers. Without dampers, we cannot think about the smart and so big city. So we have to follow the development of the new devices that can be used in our buildings and other structures. I think our participants may have more query when they exercise on that, and in future they may need help
Yes,
from the
really
Sandeep
fine.
ji.
How about you,
So
sir?
in future, may we request Sandeep ji to elaborate more or clarification on the query of our designers, and if possible, we can physically meet and listen one more lecture from the Sandeep ji. And at last, I want to wish a very happy Vijayadashmi to all of our participants and our guests. Thank you all.
Yes.
And this is the end of the program, and I
Yes,
want
yes.
to
All
announce
of
one more thing
the
in
engineers and
November.
architect have returned.
In
So
November
no
19
one,
and
is
27th,
here
we have the
currently.
two programs. November,
the thing
November
is-
27th is the
No
SEANep
one's
Day,
here.
and probably
the
19th will be our AGM day. On both
So the
days,
thing,
we
I think
are going to
the
arrange
last
some
day
programs
for
to
them,
all participants.
I think it was
Now
the 5th.
I want to inform you that
I think it
please
was. I think it was
contact,
the 5th
be
of
together with us.
October. That was
we
the last date in
accept
which I think Kawai-san,
today's
I think
participants now.
Shiraishi-san too,
programs.
and
Thank you.
a few of them.
Thank you, Sandeep ji, and thank you all
Thank you.
participants.
Thank you very much.
So,
It was an honor.
prior to
Thank
that,
you.
Thank you, Sandeep, for
to
presentation.
5th, I think some of them
Thanks,
left
everybody. Bye.
before that also. I think Kyoa-san also left at 5th.
Always, I think I understand. And I'd like to know, how about the content of guideline? Is it already fixed after the meeting?
No, content of the guidelines from the DODBC side or from the client side?
No, from the DVC side. Did they have some comment?
Recently, the thing is the clients have I think the DODBC have been provided with the content table of content from the sub clients of sub consultants ERTech. They recently changed one according to the stakeholders, and the thing I think they have been provided. The table of content was only provided the day before, I think yesterday,
Really?
and they have yet to like review the table of content, recently made table of content. So I think the work will they will only review the table of content after the holiday has ended.
Okay, I understand. So could I have meeting again after the holidays? Because maybe in this next week I'm also very busy and have no time to spend the. I'm sorry, but I have no time spending the Nepal project.
Yes,
and
okay, it's
if
okay.
possible, I'll have to meet with you after the time.
Yes,
holidays.
certainly, Fukushima-san. Certainly, yes. We can have
Yeah.
a meeting. So, as I have mentioned, we have our holiday starting from today to the 17th, as today is Sunday, Saturday, and starting from today we have holiday till the 17th.
17, okay, I understand. But you know that I returned to Japan on 20. Maybe I'm after the 20th of this month
Yes.
till the November 1st. I'm in again quarantine period.
Yes,
At the time I'm very free. I may have a lot of time
Yes.
spent in the project.
Okay. So we'll work on that.
Yeah, of course. And can I ask you one thing?
Yes, yes,
About
please,
my,
Fukushima-san. Yes,
my
yes, please.
trip to Nepal. So, if possible, I'd like to spend the end of the year and beginning of the year in Nepal.
Yes.
But is it possible to have a work at the time in Nepal? Maybe December 31 or December 30 or January 1st or January 2nd. Does it work? No.
From December. Excuse me. The thing is, I'm currently looking at the calendar. So we don't have much holidays. Starting December 15th to mid of January. So I think we'll work. We can work in that time.
But usually you have the holidays and at the first of the year and the last of the year. Maybe maybe from late December to early January of next year.
No.
Usually how many days do you have for holidays?
Starting from December 15th to January 15th, we don't have much holidays. I think the only holiday we are going to get, we don't like celebrate the English New Year. so we don't have holidays right then. So I think we will have only 1 to 2 holidays at maximum in the calendar. There is no holiday actually.
Already, yeah. Okay.
December 15th to January, we don't have much holidays. So in our country we work in the English calendar, English New Year also. Only in the Nepali New Year, I think we have one holiday in the first of our Nepali month.
Oh, really? Just one day?
Only one
holiday?
Only one holiday. We don't have like the longest of the holidays that we have in Nepal is Dasai.
Okay, I understand.
Rather than that, only we also have 3 days holiday in the coming month, November. I think 4 to 6th, 4th and 5th of November. Other than that, we don't have much holidays in December and January.
Exactly, I understand. And the Holy Christian will go to Nepal January again, early January. Maybe the 5th to February 5th, I don't know exactly. If possible, I like come to Nepal with Holy Christian.
Yes.
Or a little bit earlier.
Okay, thank you.
Okay. I'd like to know in the past, quarantine period, you still need it?
I don't know the current rules of the quarantine, but I think Kawai-san had to stay in the hotel for like 10 days, 10 to 12 days. But I think as the number of like COVID patient has been like reduced drastically, we don't. Yes, it has been reduced to I think 1,000 per day only. I think previously it was like 10,000 or something. It has been reduced to like 10 times. So I don't think we have like that strict rules. So currently I don't know the exact rules for quarantine. So I think